Petroleum refinery, also referred to as an oil refinery, is an industry that facilitates an intricate process involving the transformation of unprocessed petroleum into refined products like gasoline, diesel, jet fuel, lubricants, and various petrochemicals. Petroleum refineries are vital components of the global energy industry as they fulfill the demand for transportation fuels and provide essential raw materials for numerous industrial sectors. The economic impact of the refining sector is significant since it fosters employment, generates revenue, and promotes the international commerce of petroleum products. The significance of petroleum refineries lies in their crucial role in safeguarding energy security, as well as diversifying and optimizing crude oil resources, enabling the extraction of a wide array of valuable products. They offer the necessary flexibility to produce fuels of varying grades and formulations, effectively meeting the specific requirements of different sectors and markets. This adaptability becomes indispensable in effectively managing supply disruptions arising from geopolitical tensions or natural disasters, thereby ensuring stability within energy markets. The refining industry's efficient conversion of crude oil into essential energy products makes a substantial contribution to enhancing international energy resilience and economic expansion.
Rotating equipment such as compressors, turbines, pumps, and others are the most critical for processes in all refineries and large petrochemical plants. Refinery often consists of tankage, a distillation unit, a recovery facilities for gases and light hydrocarbons, and the necessary utility systems such as steam, power, and water treatment plants. A refinery must be equipped with proper tank facilities. The tanks are used to store raw materials and already refined products. When there are enough tanks in the refinery, there will be a continuous flow of operation as crude oil will be easily collected from the oil well and transferred into the necessary tank required for processing simultaneously. Flare is built in the form of a tall stack with flames burning at the top. This equipment is very important for the plant's safety as volatile hydrocarbons can be explosive when exposed to air. In the event of equipment failure or plant shutdown, it is necessary to purge the volatile hydrocarbons from operating equipment so that it can be serviced. A sophisticated refining machine built along pipeline routes, the transported material will get enough pumping power to reach its destination. A sophisticated refining machine built along the heat exchanger is a thermoregulation equipment primarily used to disperse excessive heat and regulate temperature during processing. The first media is the liquid or gas being processed, while the other media is the heat-absorbing coolant made up of chilled gas or liquid. The distillation units ensure liquid and vapor contents are separated into fractions. After attaining a certain boiling point, heavy fractions stay at the bottom part, while light fractions stay above. Petroleum and gasoline, which are the lightest form of fraction, rises to the top of the distillation unit to be condensed back into liquid. Cracking is the most common form of conversion because it is powered by catalyst, pressure, heat, and maybe hydrogen. In this process, heavy hydrocarbon molecules are cracked into lighter ones. The cracking unit is made up of a thick-walled reactors, heat exchangers, and chain of furnaces and many other types of vessel. Reactors are containers intended to execute chemical reactions between reactants and feedstock or reactants in multiple feed streams in the presence of a catalyst. Reactors are containers intended to execute chemical reactions between reactants and feedstock or reactants in multiple feed streams in the presence of a catalyst. Each refinery is uniquely designed to process specific crude oils into selected products. In order to meet the business objectives of the refinery, the process designer selects from an array of basic processing units. In general, these units perform one of three functions. Number one is separating the many types of hydrocarbons present in crude oils into fractions of more closely related properties. Second is chemically converting the separated hydrocarbons into more desirable reaction products. And the third is purifying the products of unwanted elements and compounds. For separation, we have first the fractional distillation. The primary process for separating the hydrocarbon component of crude oil is fractional distillation. Crude oil distillers separate crude oil into fractions for subsequent processing in such units as catalytic reformers, cracking units, alkylation units, or cokers. In turn, each of these more complex processing units also incorporates a fractional distillation tower to separate its own reaction products. The principles of vacuum distillation resemble those of fractional distillation, except at larger diameter columns that are used to maintain comparable vapor velocities at reduced operating pressures. The primary advantage of vacuum distillation is that it allows for distilling heavier materials at lower temperatures than those that would be required at atmospheric pressure, thus avoiding thermal cracking of the components.
Absorption. Absorption processes are employed to recover valuable light components such as propane or propylene and butane or butylene from the vapors that leave the top of the crude oil or processing unit fractionating columns within the refinery. These volatile gases are bubbled through fluid, such as kerosene or heavy naphtha, in equipment resembling a fractionating column. The light products dissolve in the oil, while the dry gases, such as hydrogen, methane, ethane, and ethylene, pass through undissolved. Solvent extraction. Solvent extraction processes are employed primarily for the removal of constituents that would have an adverse effect on the performance of the product in use. An important application is the removal of heavy aromatic compounds from lubricating oils. Removal improves the viscosity-temperature relationship of the product, extending the temperature range over which satisfactory lubrication is obtained. Adsorption. Certain high-porous solid materials have the ability to select and absorb specific type of molecules, thus separating them from other materials. Silica gel is used in this way to separate aromatics from other hydrocarbons, and activated charcoal is used to remove liquid components from gases. Crystallization. The crystallization of wax from lubricating oil fractions is essential to make oil suitable for use. The wax crystals are removed from the cloth by metal scrapers after washing with solvent to remove traces of oil. The solvents are later distilled from the oil and reused. And now, for the second part of the process, which is conversion. First is naphtha reforming. The most widespread process for rearranging hydrocarbon molecules is naphtha reforming. By 1950, a reforming process was introduced that employed a catalyst to improve the yield of the most desirable gasoline components while minimizing the formation of unwanted heavy products and coke. A catalyst is a substance that promotes a chemical reaction but does not take part in it. In catalytic reforming, as in thermal reforming, a naphtha-type material serves as the feedstock, but the reactions are carried out in the presence of hydrogen, which inhibits the formation of unstable, unsaturated compounds that polymerize into higher boiling materials. Next kind is the catalytic cracking. The thermal cracking process functioned large. The next kind is catalytic cracking. The thermal cracking process functioned largely in accordance with the free radical theory of molecular transformation. Under conditions of extreme heat, the electron bond between carbon atoms in an hydrocarbon molecule can be broken, thus generating a hydrocarbon group with an unpaired electron. This negatively charged molecule, called a free radical, enters into the reaction with the other hydrocarbons, continually producing other free radicals via the transfer of negatively charged hydride ions. Thus, a chain reaction is established that leads to a reduction in molecular size or cracking of components of the original feedstock. The result is a weakening of carbon-carbon bonds in many of the hydrogen-carbon molecules and a consequent cracking into smaller compounds. Polymerization and alkylation. The light gaseous hydrocarbons produced by a catalytic cracking are highly unsaturated and are usually converted into a high-octane gasoline components in polymerization and alkylation processes. In polymerization, the light olefins propylene and butylene are induced to combine or polymerize into molecules of 2 or 3 times their original molar weight. The alkylation reaction also achieves a longer chain molecule by the combination of two smaller molecules, one being an ophyline and the other as an isoparaffin. Next, hydrocracking. One of the most far-reaching developments of the refining industry in the 1950s was the use of hydrogen, made possible in part by the availability of hydrogen as a byproduct of catalytic reforming. Though hydrocracking processes possesses a similar feedstock to the catalytic cracking unit, it offers even greater flexibility in production yields. The process can be used for producing gasoline or jet fuels from heavy gas oils, for producing high-quality lubricating oils, or for converting distillation residues into lighter oils. Last type of conversion processes is the isomerization. The process of isomerization used in the refinement of petroleum raises the octane rating of gasoline. This is accomplished by transforming straight chains of paraffin molecules into isoparaffin branched forms. This method of raising the octane rating is significantly more efficient and refined. And now, for the third part of the basic refinery process, purification. So before petroleum products can be marketed, packaged, certain impurities must be removed or made less obnoxious. The most common impurities are sulfur compounds such as hydrogen sulfide or mercaptans, the latter being a series of complex organic compounds having as many as 6 carbon atoms in the hydrocarbon radical R. Apart from their foul odor, sulfur compounds are technically undesirable. Most crude oils contain small amounts of hydrogen sulfide, but these levels may be increased by the decomposition of heavier sulfur compounds such as the mercaptans during the refinery processing. Other undesirable compounds include nitrogen compounds, which poison catalytic systems, and oxygenated compounds, which can lead to color formation and product instability. First kind of purification is the sweetening. So this processes oxide mercaptans into more innocuous disulfides which remain in the product fuels. The oil is heated and brought into contact with the slurry while being agitated in a stream of air that oxidizes the mercaptans to disulfides. The slurry is then allowed to settle and is separated for use. A heater raises the temperature to a point that keeps the water formed in the reaction dissolved in the oil, so that the catalyst remains properly hydrated. After sweetening, the oil is water washed to remove any traces of catalyst and is later dried by passing through a salt filter. Next is mercaptan extraction. Simple sweetening is adequate for many purposes, but other method must be used if the total sulfur content of the fuel is to be reduced. And one of this kind is the mercaptan extraction, which is almost the same with the sweetening process. Third is clay treatment. Some natural clays, activated by roasting or treatment with steam or acids, have been used for many years to remove traces of impurities. The phenomenon is similar to that described under the absorption processes, wherein the clay retains the longer chain molecules within its highly porous structure. However, the problem of dealing with spent clay now designed as a hazardous waste in many places, has led many refineries to replace clay treatment facilities with a mild hydrogenation process. This then leads us to hydrogen treatment, which is commonly known as hydrotreating, and is the most common process for removing sulfur and nitrogen impurities. In here, the oil is combined with high purity hydrogen, vaporized, and then passed over a catalyst such as tungsten, nickel, or a mixture of cobalt and molybdenum oxides supported on an alumina base. The sulfur in the oil is converted to hydrogen sulfide and the nitrogen to ammonia. Operating conditions are set to facilitate the desired level of sulfur removal without promoting any change to the other properties of the oil. Last is the molecular sieves. Molecular sieves are also used to purify petroleum products since they have a strong affinity for polar compounds such as water, carbon dioxide, hydrogen sulfide, and mercaptans. Sieves are prepared by the dehydration of aluminosilicate such as zeolite.
To summarize all the facts stated earlier, petroleum refining breaks crude oil down into its various components, which are then selectively reconfigured into new products. They follow three basic steps: separation, conversion, and treatment or purification. For separation, discharging liquids and vapors into distillation units. Inside the distillation units, the liquids and vapors separate into petroleum components called fractions according to their boiling points. The lightest fractions include gasoline and liquefied refinery gases, vaporize and rise to the top of the distillation tower where they can condense back to liquids. Medium weight liquids include kerosene and distillates stay in the middle of the distillation tower. Heavier liquids called gas oil separate lower down in the distillation tower, and the heaviest fractions with the highest boiling point settle at the bottom of the tower. For conversion, after distillation, heavy lower value distillation fractions can be processed further into lighter, higher value products such as gasoline. At this point in the process, fractions from the distillation units are transformed into streams intermediate components that eventually become finished products. Methods of the conversion include cracking, alkylation, and reforming. For treatment and purification, the finishing touches occur during the final treatment. To make gasoline, refinery technicians carefully combine a variety of streams from the processing units. Octane level, vapor pressure rating, and other special considerations determine the gasoline blend. The common petroleum products are gases, gasoline, kerosene, diesel oil, lubricating oils, and purified naphthas. Gaseous refinery products include hydrogen, fuel gas, ethane, propane, and butane. Gasoline is a volatile, flammable liquid mixture of hydrocarbons obtained from petroleum and used as a fuel for internal combustion engines and as a solvent. Kerosene is a combustible hydrocarbon liquid which is derived from petroleum. It is widely used as a fuel in aviation as well as households. Diesel fuel, also called diesel oil, is a combustible liquid used as fuel for diesel engines, ordinarily obtained from fractions of crude oil that are less volatile than the fractions used in gasoline. Lubricating oils, or sometimes simply called lubricant or lube, is a class of oils used to reduce the friction, heat, and wear between mechanical components that are in contact with each other. Purified naphthas is used for solvents in paints, cosmetics, and dry cleaning.
By 1970, the global petroleum refining industry had established itself firmly, with the delivery of crude oil for refining into petroleum products reaching nearly 2.3 billion tons per year, equivalent to 40 million barrels per day. However, as the world became increasingly aware of the environmental impact of industrial pollution, the petroleum refining industry became a focal point for change. Petroleum refineries are essential for meeting global energy demands and providing a wide range of refined products that are vital for transportation, industry, and daily life. These refineries have undergone significant changes to address environmental concerns and comply with regulations. Petroleum refining is presently one of the industries with the strictest regulations worldwide. They have adopted advanced technologies and stringent measures to mitigate pollution, reduce emissions, and minimize their ecological footprint. While processing over 4.6 billion tons of crude oil annually, or about 80 million barrels per day, it devotes a considerable percentage of its resources to minimizing the negative effects on the environment. By prioritizing sustainability and continual improvement, petroleum refineries strive to balance energy needs with responsible environmental practices. While the world moves towards cleaner and more sustainable energy sources, petroleum refineries remain crucial for efficient crude oil utilization and the ongoing pursuit of a greener future.